Okay. Are you all able to see my screen?
Yes, sir.
Yes, sir.
Great. Thanks. Okay. So let's go ahead with our time frequency analysis methods. So we had posed three questions when we started our LFP segment uh, many classes ago. We answered the first question where we saw that the stimulus induces a strong gamma oscillation in the signal. Now I want to know whether these gamma oscillations, the power or frequency of these oscillations change. So for that, I need to do time frequency analysis. So we looked at short time Fourier transform in the last class. Here the idea is that you take a window, and it could be a Hamming, Hanlang, whatever you want. Gaussian is what's shown here. And you multiply the signal with the window to get a windowed signal like this, and you compute its Fourier transform. So when you compute its Fourier transform, you will get lots of values, and you know um, as a function of frequency. So you can think of those values as tiling your y dimension here, and you'll get one set of values, and then you move your window and repeat the procedure. Okay, so you will end up getting now um, the Fourier transform as a function of omega, which you had earlier obtained in previous analysis, but also as a function of tau, where tau determines where this window is placed. Okay, so as you are shifting tau, you're just moving the window away, and this thing is called the short time Fourier transform of the signal. So we saw some examples. This is a single, individual trial, the duration of which is, I think, minus 0.1 to 0.5 seconds. And you can apply a window whose length is 256 milliseconds, and then compute the Fourier. So suppose the window is placed here at the center, and then you compute its Fourier transform. So you get values as a function of frequency, now shown here. And the value, the amplitude is shown by the color. Okay, so the reddish color indicate more power. In this case, it's amplitude. Bluish color means less power. And then when you move the window, you get another set of values, and so on. Okay, and to note here is that the boxes that you see have a finite area, has a minimum area. It can't be arbitrarily small in both time and frequency domains. If you reduce the window size so that now it's 128 milliseconds or 64 milliseconds, then your area length on the y-axis increases. So it's as if you've got some tiles to tile the time frequency space, but the product of the length and width cannot go below 1. Okay, so if you try to squish it in one dimension, it will elongate in the other dimension. So when you use longish tiles, you've got good frequency resolution in tiles shown here. These got good time, poor time resolution, but good frequency resolution. And these ones have got good time resolution, but poor frequency resolution. So in a single trial, they all look very, meaningless. But if you have lots of trials, like 76 trials we had, we could take the average of those 76 trials to get the ERP. But we could also get the average of the 76 amplitude spectra. And that is shown here. And now you can see the gamma rhythm here. Hope everyone can see this. We will do some more analysis to make this more prominent. But I hope you can all see the gamma rhythm here. But there's also a transient that's related to this initial depolarization that you can't see very well here. That's getting washed out because it's very localized to a particular time, but you are sort of averaging it out over time. Okay, so you have sacrificed your time resolution, so you can't see it very well. That you can see better. That you can see much better in this kind of a plot, where you are using a shorter window here. Now you can see this increase here, which is quite localized. It's occurring about at the same time as this, but now you can't see the oscillation very well. So you can almost think it as if you're painting the time frequency plot, but you can either use horizontal brush strokes or vertical brush strokes or somewhere in middle. You have choice between these. But if you are using horizontal brush strokes, then you are going to wash out anything that is very transient, like what's shown here, but you will capture the oscillations properly. Likewise, if you are using vertical brush strokes, then you are going to wash out the oscillation, but you will get the transient properly. Okay, so it's a trade-off between time and frequency that we see. That's like the hallmark of all time frequency, all of signal processing actually. I mean, you can't have simultaneously good time and frequency characterization of a signal. Okay, so is this fine? Can I move on? Are there any questions?
In the middle graph, in the middle plot, I think both sort of transient as well as oscillations are visible.
That's right. That's because it's intermediate time and intermediate frequency resolution. So it's poorer than the transient that's seen here, and it's again poorer than the oscillation that's seen here. So if you want to capture both, you would choose a middle ground and choose sort to capture both. So yes, a good strategy would be to use an intermediate length signal like 128 milliseconds and then compute it that way. That way you can get a bit of both, but neither as good as a long window here for oscillations, nor a good short window for transients as shown here. So it's a compromise. Okay, so I will now talk about a common framework to think about these time frequency analysis techniques, which will hold for short time Fourier multi-taper method as well as wavelet transform, which I will do today. And the interpretation is that of a filter bank. So what you can think of this is a series of filters that are applied to the signal. Okay, so what is a filter? Filter is just a function that sort of captures a particular the properties of the signal at a particular time and a particular frequency. Okay, so when we say a band pass filter between essentially I am saying let me look at the signal between 50 and 60 hertz. Okay, so I want to look at the 50 to 60 hertz component of the signal. That's what a filter is going to do. It's going to filter out everything else and show you just the signal, the component of the signal between that particular frequency, 50 to 60 hertz. A low filter is one only shows the lower frequency components. It filters out everything that's at higher frequencies. Pass filter does the opposite. Band pass filter filters some range. So we think of a so by the way, the windows that I had shown, just to make this clear, These are all low pass filters. The window by itself is always low pass because it's only allowing this particular range of frequencies to pass. Everything else goes away. Okay. But now, when I think of computing the Fourier transform, a windowed Fourier transform, I guess we'll just look at it here. So forget about tau here. It's xt, ht, e to the power j omega t dt, right? So this ht multiplied by e to the power minus j omega t, this is now a filter which is low pass here, but it's translated by this frequency. So it becomes a band pass filter. If I didn't have this ht at all, I would be thinking of a rectangular filter sitting at omega here. Okay, so this is how I think of this. This function here is nothing but the inner product or a point by point multiplication of the signal xt multiplied by the window and this function e to the power minus j omega t, which is essentially just a sinusoid and a cosine, sinusoid with a phase. So this function as a whole is like a filter. So the way to think of it, and uh, please pay attention to this. This is very crucial in the development of what we are going to do. The idea is that you make these boxes, so you divide your time frequency space into small tiles, and you have to think of as if each tile is home to one function, which is now shown here. It's the product of the window, which is the same shape here, multiplied by complex exponential, which gives it this oscillatory thing. Okay, and essentially what I'm checking here is how well is my signal xt matching with this windowed function here. That's the inner product. Okay, if the signal actually is oscillatory like this right here, then this integral will be a large value. If you are uncomfortable with the integral, think of it as a summation, okay, which is what you would do for a discrete signal. So in the summation, it's just xt multiplied by h prime t. Forget about tau. So it's a dot product. It just tells you how well things match with each other. And if two signals are very similar, the dot product is large. Otherwise, it's small. So the way to think of time frequency analysis is that you have these little tiles. Within each tile, you've got a function that's sitting. And I'm just taking the inner product of my signal with that windowed, with that function. And the value of the inner product is then shown as a color on this tile. The larger is your inner product, the reddish it is, the smaller is your inner product, the more bluish it's going to be. Okay, so it's like a bank of filters that is applied to the signal xt, and you are looking at the output of the filter x omega tau here, tau omega in this case, as the output of this filter bank, the amplitude of which is then shown as a color plot like this. Okay, is this interpretation fine? A very convenient interpretation, which we will see will make life very straightforward. Okay, so I'm going to ask some hard questions based on this, and I think a lot of the sort of confusion about this interpretation sort of is addressed by those questions. So are you guys ready for it, or do you have any questions on this interpretation itself?
So correct. So correct me if I'm wrong. Here means each tile contains a band filter, and then
No, each tile contains one filter.
Okay.
The bank, because there are a lot of these filters.
Yeah. So at each time point, the current sorry, the current, I mean to say the signal itself is getting having an inner dot product at one tile, and according to the frequency, the value changes. Right.
That's right. So according to the frequency, it's a different filter. So this is one filter, that is one filter, this is one filter, and so on. Okay, and you're taking an inner product with each one and getting one value, which is the filtered, which is the inner product of the signal with that filtered. Okay, so for each time point, there are lots of filters, one for each frequency. As you go up, you will see one set of tiles. And then when you move the window, you'll get another set of tiles. So even Fourier transform that way is just a filter bank. It's just, a sinusoid, complex sinusoid is your filter. You can think of it multiplied by a rect function if you don't have this. So even Fourier transform has a filter bank interpretation that way. So you are always looking at different frequency components of the signal, right? So in that sense, you're always looking at as if there are different filters that are looking at different frequency. So a pure sinusoid is also a filter. Here it's a windowed sinusoid, but you also shift the window. So that's how you create a large bank of filters.
So so then it doesn't matter on the value of tau, right? Means, but
No,
if I
no,
change the
as
value
you
of tau,
change
so the
tau, you are looking at a different part of the signal.
okay.
So XT is this long signal here. As you change tau, you are looking at a different part of the signal. So this is your HT, and then as you change tau, it translates. So you are looking at different parts of the signal and computing its FFT to get the filter on along the y-axis. That's the frequency axis. So changing tau will translate the filter along the time dimension.
So
Okay,
in general, the plots that you shown, when you move from left to right, the plots will be changing. Matlab, though I found them very similar. If we say the left extreme below and right extreme below, the down one, they are looking similar, but for a general arbitrary signal, they would be different.
No, 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 no. So what I'm showing you here is not the signal. What I'm showing you is the filter. The filter is exactly the same. It's just sitting at a different location. Okay, so this thing and this thing is exactly the same. It's just h t minus tau multiplied with a sinusoid. This sinusoid is the same everywhere. So if you think of this sinusoid, it's a constant sinusoid throughout this time axis, and this window location just highlights that. It makes everything else zero. Okay, so this thing and this thing are identical except a translation in time. Now you're multiplying it with a signal which is varying over time.
Okay.
Okay, does that make sense?
Yes.
So, yeah. One second, let me. Um, 1 second, let me get my. Wacom pen. So here, when I this is the signal. When I say I want to just compute the Fourier transform, essentially I've got a sinusoid, a complex sinusoid, and I take the inner product of x with that sinusoid. Okay, and that's just xt sine, well, e to the power, it's a complex sinusoid. This is the Fourier transform. Now, when you do this, you don't know where, and you get one value at, let's say, 50 hertz or whatever, and it just tells you that's the average power at 50 hertz. It doesn't tell you where it is. This is a perfect sinusoid. And if you take the inner product of this with this, you just get the Fourier transform. Now you can apply a window at one point like this, and then the product of this with that is your this signal like this. That is what I am drawing here, this thing. Then you are again taking the inner product of this signal with this window, but it's going to only care about what it is at this point, because the rest of the time it's all zero. So now when you compute the Fourier transform, it is the Fourier transform corresponding to this particular location in time. Now this is a windowed Fourier transform, and think of it, this is now your filter. This thing is your filter. And you are going to translate the filter to a different location. So the filter will look like this, and you compute the Fourier transform again, which will to this weird thing. Click and double click. It's gone. And then it will give you another value which corresponds to the properties of the signal at this time. So the signal is varying, the filter is the same, it's just getting translated. So this thing and this thing are the same shape, it's just translated in time, but the signal is changing, the signal is different. So the signal here is not the same as the signal there, which is why the values that you see when you take the inner product of this with this and this with that are different. You're taking, it's the same signal, you're taking an inner product with this and it gives you one value. That value you color code and put here. Then you take the inner product with this, with the inner product with that, and so on. And that will make one like this. And as you translate, you get different rows. Okay.
Yes, sir.
Okay, so yeah, so this is the filter bank interpretation. So this is my window. So by the way, this is the paper I was telling you about. This is my former student, master student, Subhash Chandran. So it's a tutorial slash, toolbox for running a complex technique called matching pursuit that we will get to in some in a few classes, maybe next class. So if you read this, it's a very sort of easy to understand paper. It's meant for biologists who haven't done much of signal processing at all. So you'll find it, and the stuff is what I'm telling you in class today. So easy to understand. Reading this paper will really help. So the idea is that the signal that you have is shown in blue here. This is my signal. After time, there's this transient, and then there is this oscillation for 400 milliseconds, then it disappears. When I apply a window, so I've applied a window here. That's the window, and I'm translating the window. The filters, which I'm also going to call basis functions here, because my signal is represented as a sum of these complex sinusoids. Those functions are just the window multiplied with the complex sinusoid. So, in the time frequency space, this particular basis function is actually this sinusoid. That particular one, it's a higher frequency. That's just this. This particular one is that. So you have got a ton of these functions sitting in this time frequency space, one function in each tile. And all you are doing is checking how well is my signal here, this part matches with this oscillatory part. And you can see that, hey, it's not much of a match. So the value that you are going to get here is low, bluish. If the signal did have an oscillatory component here, then you would have seen a strong value there. Like for in the gamma range, you see a strong value because there is an oscillatory component. See that? There's the oscillatory component, which then produces a strong, large value here. This is how a plot like this is able to show the emergence of gamma rhythm. You can say that the gamma is only strong at this particular location, which you can see in the signal. See this going up and down at about the same frequency as this filter. Likewise, this dip here and this thing here sort of produce a big signal here. It's capturing the transient. So this is the filter bank interpretation of the spectrogram. Does that make sense? Pretty neat, actually.
Yes, sir.
Okay, so now let me ask some hard questions. They're not straightforward, but I really want you to think and think, even if you're wrong. So one question is that what I'm showing you here are all real signals, right? But what I'm telling you are complex sinusoids, like so. Right? Now, you may ask if these filters are fixed here, okay, and it's a real signal and it's a real signal here as well. How do I how do I represent the phase signal? So, for example, I had a pure sinusoid as my signal. So, it's a pure sinusoid. Okay, so when I overlay it, and let's say it's just this frequency, so inner product with everything else will be 0. So when I overlay it, it will be like this, and the inner product, because the dips and the troughs and the peaks align, the dot product will be some large value. But I could also think of a slightly shifted sinusoid which would have an inner product of 0, or a sinusoid which will have an inner product of -1, because it will depend on the phase of the signal, right? If I just translate it a little bit, it can fall out of phase or in phase, or have an inner product of 0. So somehow the information about the phase or how much this sinusoid is translated with respect to this sort of arbitrarily defined position of the oscillation, that needs to be captured. How do I do that? In fact, this is why you can't just have one sinusoid, which is as shown here. You need to have a complex sinusoid which catches the phase. But in terms of real signals, how does it happen? This is a very hard question, by the way. So feel free to guess without, if you get it, it'll be quite cool. So guess away. What do you think this thing is doing? Whatever I'm telling you right now, by the way, is not just for short time Fourier transform. It holds for Fourier transform as well. Just forget about this bit here and think about it from Fourier transform point of view. When I compute the Fourier transform, how do I account for the phase of the signal?
One thing we can do is that since here we are plotting the real signals only, so we take the absolute value here, right? And then so we can match with whichever the frequency we get the maximum power, then we can say that at that frequency we can get a particular phase, and that phase matches with the given frequency.
Yeah, no, but there's no phase in picture. There's just one real signal here, and you're taking the inner product with a real signal, and it's a real filter. So you're
No,
just going to get some number.
yeah, so I mean at that power means at that frequency, no, it varies with time also. Sorry. Yeah.
Okay, so the way to think about it, let me, so somebody is trying.
Yeah,
Go
I
ahead,
just
go ahead.
guess. Like it's just like mathematical interpretation. When we have
Hmm.
suppose e power minus j omega t, it has two components. One is the
Hmm.
real part like cos, and the other is the sinusoid. Okay.
Hmm.
So now if we have a real signal, if we convert it into like e power j omega t kind of thing, means
Hmm.
and assume that the signal is itself the real part of it.
Okay.
In that way, we'll have a signals interpretation as the real part of e power j omega t kind of thing. Matlab, it's omega is something, omega is different from this omega, and then we can account for the phase.
Yeah. So that's right. Very good. I think you started properly. There was some in the later part. But the concept is right. So see, when I take the Fourier transform, let me just go back in time and just get to the Fourier transform. 1 second. Um, um, this is delta function, sample, impulse function, impulse, where's Fourier transform? LTI. Yeah. So right now, this is the Fourier series interpretation. And we saw that each signal can be broken down as ak e to the power j k omega naught. But the key to note here is that you could also represent it as a sum of sines and cosines. Okay, only sinusoids won't work. You need to have sines and cosines. So E j k omega naught t can be written as cos k omega naught t plus j sine k omega naught t. So your xt would be represented as a summation of some coefficients with this plus some other coefficients with this. Okay, and here it's just I have put this as that, and then AK is your AK prime, and then J times AK on the other side would become this. Okay, so you can either represent it as a sum of complex exponentials, or as a sum of both a sinusoid and a cosine at that frequency. So you can either represent it as sum of two sort of real signals that are sort of complementary to each other, um, or as a single complex sinusoid. And also a third interpretation could be as a sum of a cosine. Let me just write it here as a xt as a sum of cosines, but with the provision of having a phase. Okay, so you can either think of your basis function, or the the set of functions of which you are you're decomposing the signal as a sum of these. They could be either complex exponentials, or a sine and a cosine with no phase, or equivalently a sine with a frequency and a phase. Okay, and they are all equivalent to each other. When I break this down, it will become cos k omega naught t sine. So it's like cos A plus B is cos A, or whatever it is, cos A sine B plus. Oh no, sorry, that's a different thing. That's cos A multiplied by cos B. So that's not right. But so this interpretation also holds. Essentially, you could either do it as a complex exponential with some phase, which is captured here, the complex term here, or as sine or cosine. Okay, so in this case, and for a real signal like this, a sine, for example, I could have broken it down as two complex exponentials. One sitting at the minus frequency and one at the plus frequency. This is what I had shown ago. I guess it's so long that you've forgotten. But here, when I say it's a single filter, actually it's strictly not true. There are actually two filters. One which is a cosine multiplied by the filter window, one which is a sine. And you're taking a dot product with both. Okay, and the phase that I talk about is obtained from the relative contribution of the real part, which is the cosine, and the imaginary part, which is the sine. Or equivalently, you could think of a filter, a single filter, but you are allowed to shift the phase. They are both valid and equivalent representations. Okay, so that is how you are able to actually get to the phase of the Fourier transform here. So just so that it's clear, you have to think of it that in each tile you have got two filters. Let me just draw you the second one here. This is a cosine, so the other one would be a sine. So it's shifted by 90 degrees. Didn't draw it very well, but you get the idea, right? So you're going to take an inner product with both the cosine and the sine. And then either you can think of two filters sitting here and then you get an inner product with the cosine, and let's say it's a1, and the inner product with sine, that's b1, and amplitude is just a1 square plus b1 square square root, and the phase is just tan inverse b by 1. Okay, so you could get both amplitude and phase by thinking of having two filters that are sitting inside, or you could just think of this function as a filter whose phase can vary. So even if you have a signal that is not in correct phase, you will still be able to capture it. And this interpretation holds not only for short time Fourier transform, it's true for all gauge. That is why you have a complex one, which has both a cost component. Okay, so you need two orthogonal, these are orthogonal functions, their inner product is 0, to capture the possibility that the signal even might occur at a different phase from where this is. So that's why you need to have both. Does that make sense?
Yes.
Okay. And Srishti, I think you got the most of it right. Towards the end, you were just saying we should look at the real part. That's not the, you need to have both parts, but together these two functions will capture both the frequency component as well as relative changes in phase or the translation part. Once you have these two, you are guaranteed to capture everything. Okay. So this is a tricky part, which I will talk in the next class. Let me actually tell you, ask a different question. By the way, is the first question important part in their our full understanding of how the Fourier idea of the representation of the phase? It's okay with everyone, right? Can move forward now. Okay, so let me ask a different question. And the question is, what if here the windows are non-overlapping, right? So I've got a window like this, I've got a window like that, and so on. What if they were not overlapping? So my next window is just like this and like that. So what if I had highly overlapping windows? How would this spectrogram look like? First of all, would I have poorer frequency resolution on this side? Or is it going to be the same? What is this tile width dependent on? This width here, what is it dependent on?
The time interval and the frequency.
No. Is it dependent on the frequency? Is the
No,
width different for this frequency versus that? No, right?
no,
It's the
no.
same width.
Mm-hmm.
So what is this width dependent on?
No. A,
Dependent on this, the length of the window, right? The longer is your window length, the thinner is your width. The product of this and this is 1. Okay, there are more nuances to this, which I'll cover in the next class. But as a first EA, you can say that if I compute the FFT over 200 milliseconds, I get a resolution of 5 hertz. If I make it 1000 milliseconds, then I'll get 1 hertz. If I make it only 64 milliseconds, I'll get, or 50 milliseconds, I'll get 20 hertz. So what I'm doing here is a little bit of a trick where I'm taking a long window, thereby making sure that the tile is very thin, but then I'm not going to the next non-overlapping segment. I'm just taking very small segments. Even here, there's a 50% overlap. See, this is 0 to 256 is here. So my actual window has a length of 256. Okay, so it's a longish sort of window like this, 256. But the next one, I haven't made a full separation. There is some overlap. What I have to know is what happens if I reduce the overlap. Then I will get good time resolution as well as good frequency resolution, or not. That's the question. So if I take a very longish window, thereby having thin tiles, and only take baby steps, then I will certainly have different values for different, at each point, wherever I'm, it's a long window, but if I translate it a little bit, I'll get a different set of values. But am I actually truly improving the frequency time resolution by taking baby steps? Note that in this case, this tau could be anything. In fact, in the short time, in the continuous domain, it's a continuous function. So you actually don't wait for this, if it's a long window, the next one is not the length of the window. The tau is not such that, it's here and then the next window is there, the way I had drawn it here. The tau is obtained by just translating a little bit. Tau could be as small as you want. So my question is, does that really improve my time resolution? And if not, why not? Again, just guess. You don't have to get it right, but that way, we'll hear some answers.
I think it's no, because like since we discussed it like just a few minutes ago, it totally so we are taking inner product which are depending upon the signal and the h of t minus tau into the sinusoid frequency. So that's why means even if we change the value of tau, we would get so overall the area will be compensated and we will get the same frequency and time versus plot. I think so.
Well, it won't be the same. So here, these are non-overlapping windows. So if I had taken a baby step, the next one would have been very close to this. A slightly translated version of this. But the point is that the inner product with this signal and with this filter green and with this black filter, the inner products are not going to be very different from each other.
Yes.
These two functions are not orthogonal to each other. They are actually highly overlapping functions. So what you will end up doing if you take baby steps is just you're going to get a smoothened representation of this rough plot, but you won't have better time resolution. Okay, it's like saying that, okay, I've got a sample here and a sample there, and essentially you are just interpolating. You are creating different values based on this. This doesn't improve my time resolution. I get more values, but they depend on this value and that value. Okay, so if I have got a bump in the signal like this and another bump in the signal like that, in order to capture it properly, I need to have windows that are short. If I've got a long window, it's going to just smooth out these bumps. It doesn't matter whether I translate it by baby steps or long steps. It's just going to, give a smoothened. So the Fourier transform, short time Fourier transform of this, if the signal had two little bumps like that, if the window is too long, it's just going to smear it out. Maybe a little bit here and a little bit there, but it'll be still a very smeared out signal. The only way to actually resolve the two bumps is to actually use a short window. So at the end of the day, the time resolution, which tells you how well can you resolve two different components in time, depends on the length of the window, not how you translate it. Otherwise, it would have been a trivial thing, right? You just take baby steps, 1 millisecond or 1 microsecond or whatever. Computers are fast these days. You don't improve time resolution by translating the spectrogram by short amounts. You can only improve the time resolution by using shorter windows. Okay, you will get a better looking spectrogram if you take baby steps. But it's just because the intermediate values between this point and that point are interpolations. They are not independent because the underlying basis functions are highly overlapping. They are not orthogonal. So it's as if you get this point and this point that represent, two different components, and the rest are all just filled in versions of this and that. So it doesn't matter in a way. Smoothing doesn't improve time resolution. Okay, this is a concept for us to understand. Often you feel that, hey, I could have just got a better looking just by moving it a little bit at a time. But it doesn't improve your time resolution. It only smooths the spectrogram. Okay.
I understand the inner
Likewise,
product.
yeah. Tell me. Yeah, go ahead.
I understand the inner product thing, but sorry. But I'm just like confused with one small thing that if you go to the spectrogram in the last slide,
This one.
no, in the short time Fourier transform wali slide,
This one.
the back or
This.
back, yeah, in this one. So when you said that this window size means on the time axis is not exactly 256 milliseconds over here, and it has some 50%. So what are we doing here in this when you have an overlap? Because I
Yeah,
thought
so
that.
we have a so what we are doing is let me just discard this. What we are doing is that then the windows are translated by, so the next window in this case is going to be here like this. So I have one window here, one window here, one window here, one window there, one window here, and so on. So it's a window which has 50% overlap. Okay, and you will get one value for at this time. You will get another value for this time, and yet another value for this time. So it would seem that you are getting values at twice the A. Okay, so you will get twice the number of values, and it would appear, so it would have, instead of a vector of, here 1, 2, 3, 4, 5, 6, right? You will have 12 values. But the point is the value between the first and the second, so the third value which you would get here would be a smooth sort of average of this and this. It won't be an independent value. It would be a smoothed version of this, because the window here and the filter that's sitting here is not orthogonal to this and this. These two are orthogonal, so they are capturing different things. This one has some overlap with this as well as that. So even if you end up getting a value here, it's just going to be a smoothed average of this and what the values that you are getting here and here. You cannot recreate information between these two if you've got a very long window, because the inner product of the underlying basis functions is not zero. So they are actually capturing similar parts of the signal, similar features of the signal. So they are correlated, they are not independent.
Okay,
Okay,
so
does that?
in that, when we have those windows, so we don't have the size of, matlab, if we say the area of the window is not equal to 1.
It is one. Each window is one. So here, this is one, and that you can't change. But you have
No,
another one right next to it.
but when we have a representation there, you will see the half of the window, na?
No, no. So that's what I'm trying to say. You will get more values. So see, suppose you get 6 values here and whatever values there, no one prevents you. So you've got 6 values, right? So let's say this particular row has 6 values, power values. Okay. No one can prevent you from interpolating this and generating 1,000 values in between.
Hmm.
This doesn't improve your time resolution though. You're just recreating from what you already have at these 6 points. That's what you're doing when you are taking baby steps. You're creating lots of values by doing baby steps, but you're not recreating anything because these values are dependent or related to the values that you have here at the non-overlapping part. That is why
Yeah.
taking the time domain in short time Fourier transform doesn't improve the time resolution. Time resolution can only be improved if you have a shorter window.
No, that I understood, but the point I was, yeah, I was just wondering is, though we, because of the overlap, we do have multiple points, okay, and if we just compute the area between the solid line and your drawn line, the area would be less than 1, and then using that thing, we can compute how much there is an overlap between the window.
Um, so the each tile here has an area of 1 and you cannot change that.
Yeah, that's
You
true.
can have more tiles. Okay, so you can have more tiles that are like translated just a little bit, but that is not the same as having shorter tiles. Okay, so when you're computing short time Fourier transform with very small, very large overlap, you are generating more number of tiles. So it is also a form of over complete representation that I'm going to talk about. But you're not reducing the size of the tile. That you cannot do.
Okay, it's
Okay.
just we see that these are just overlap tiles. That's it.
That's it. It's just overlap tiles. So they contain redundant information about the signal because they are highly overlapping. So their inner product is not zero. So you have ended up just smoothing the signal. Interpolation doesn't improve the time resolution, right? So if I give you this and that, and the rest of the points are just between this and that, it's not that you're by interpolating you have improved the time resolution. If your signal had very small fluctuations, you would need a shorter window to capture this. Just by smoothing it, you won't get.
Got it.
Okay. Yeah, these are all very important points, practical important points that we need to worry about. Okay, so we will continue from here in the next class, and we will look at how multi-taper and wavelet transform fit into this, and then we will start talking about um, introduction to Hilbert transform. Okay, and we'll continue from there. All right. Is there any other? So class is over. Stop recording now. Is there any other